Hey folks, welcome to this episode on orbital diagrams. So what we've seen is that we've progressed from these very simple billiard ball models into the world of quantum. And so as such, we have to also evolve our way of representing the atom and communicating how the electrons are arranged in an atom. So what we are comfortable with is using our Bohr-Rutherford diagrams before. Remember, our Bohr-Rutherford diagrams had the nucleus, which show how many protons there are, how many neutrons there are, and we would put electrons into these discrete little orbits, and we'd put the electrons here, around, and etc. etc. But again, we've kind of moved away from this, where Bohr said that they behave in these discrete orbits, and we know that that's just not true. We can't actually precisely know the location momentum at any given time, as well. We can't know the position and the energy at any given time. So we moved into this electron cloud model, or the quantum model, where there's more of a probability of finding electron here. Again, movements for a little bit farther is now not only do we have these orbits, but we know that they exist in these orbitals of high probability. So the question is, how do we actually put these electrons into this arrangement, and how do we really communicate this the way that we communicated what we previously knew using Bohr-Rutherford diagrams? Now, just recall a few things. We have our four quantum numbers, the first three representing the size, shape, and orientation of our subshells, and the last one looking at the electrons. Remember, principal quantum number shown by n shows the size and energy, and it could be any positive integer. Our angular momentum quantum number shows the orbital shape, so spherical, cloverleaf, dumbbell, etc., etc. That's shown by the L value, and that value can be anywhere from 0 to n minus 1. Okay. We also have our third quantum number, which is our magnetic quantum number, and that is any value from negative L to positive L. And that shows the orientation in 3D space. And finally, our last one is our ms orbital, and that shows the electrons. Now, one thing to keep in mind when getting into this filling of arrangements is that we have to do pretty much what we did with Bohr-Rutherford diagrams, is that we always start with the innermost energy levels, or the lowest energy levels, before we can populate the higher energy levels. So just keep that in mind as we move through this. There's no difference in terms of that between what we're going to be doing and the Bohr-Rutherford diagram. Now, it does get a little bit confusing, not as straightforward as a Bohr-Rutherford diagram, where we had these distinct shells or energy levels, and even some people will say, well, I understand that we have energy levels, and that sometimes now we can break them up. So remember that, for example, this first energy level, the principal quantum number would be equal to n is equal to 1. The quantum number for L would be, in this case, 0 to n minus 1, so it would be 0. And the ml would also be equal to 0. So what we can get from this information is that the first energy level will only have one orbital type, and that 0 is going to be an s orbital. When we get into our n is equal to 2, remember that our L values can be 0 and 1. You can have s and p. And then our third shell, our values for L can be 0, 1, and 2, which is s, p, and d. Now, it's not as easy as saying that they have these three little subshells. Remember that these are geometric shapes, and they do have some overlap. Here, when we look at this, it makes things easier than it is, because we can see that this first energy level is separate from the second energy level, even though it has two sublevels, and this third one has three sublevels, but they're all kind of separated from one another. They don't overlap. The real story is something that looks like this, where we actually start having overlap of some of these energies of these orbitals. You can see this most prominently when we look at this little interaction over here between our 4s and our 3d. Logically, what we've been seeing is we go from 2s to 2p, or spd, but there's starting to see some overlap over here. Now, what is this? All this is saying is that the 4s orbital is actually of lower energy than the 3D orbital, and therefore the electrons are going to be filling as such. So this is a little snapshot of just the first four energy levels. As you go into the fifth and sixth, you're going to have a tremendous amount of overlap. So that's going to be our first little interaction in terms of that, and we're going to talk a little bit more about this as we go along. So again, here what we see is we have our first energy level, and we can only have L is equal to 0, so that's going to be 1s. L here could be equal to 0 or 1, so 0 or 1, that's going to be our S and P. For 3, it could be 0, 1, or 2. For 4, it could be 0, 1, 2, or 3. But again, you see this overlap here, the 4s and the 3d. So this translates into how we actually fill. And how we fill is using something called an orbital diagram. Now you can see that our orbital diagram that we're going to be using is going to be slightly a little bit different than this one, but you can see that as we go up into our different energy levels and orbital types, we're staggering them to show an increased amount of energy, as you can see by this arrow over here. So if we put an arrow over this way as well, we'd see an increased amount of energy. So if we could kind of read this, we'd see that the 1s orbital is the lowest amount of energy compared to everything, followed by the 2s, and that makes sense because, again, the quantum number n2 will show that it's bigger, farther away from the nucleus, means more potential energy, so it will be of higher energy. Then you're going to see your 2p's. Now what you'll see here about your 2p's is that you have your 3 orbital types, and we call these degenerate orbitals, meaning that all these orbitals in this 2p will have the same amount of energy, and that's why they're kind of on the same plane over there. Then we go into our 3s and 3p, and for the first time you see this overlap here where it should go spd logically, but we actually have this little interjection of the 4s here because this orbital has less energy than your 3d orbitals. So using our orbital diagrams is a nice way of representing how the electrons are arranged within an atom. The boxes, or maybe sometimes you'll just see lines, they represent the orbitals, and one-sided arrows, which look like this, show the electrons. So what we're going to be doing is we're going to be putting the electrons in these different orbitals to populate them based on a certain method. Now, when it comes to drawing these orbitals, you have to keep a few rules in mind. The first one is the Aufbau principle, which in German basically means to build up. So you go from the lowest energy levels to the highest energy levels, and also the orbitals in between. Hund's rule is that you have to give each orbital one electron, and that's shown by the upspin. So remember that the electron is shown by an arrow, and the way that we can show an upspin is just by pointing the half arrow up. So each orbital in orbitals or subshells that have multiple orbitals, each one will get one electron. So if we had kind of 3 spaces for representing the p, each one would get one electron before we can go back and double up if we need to. And the last thing is the Pauli exclusion principle, meaning that no electrons can have the same 4 quantum numbers. So we're going to be showing one as an upspin and one as a downspin, and we actually already showed that over here. So kind of Hund's rule and Pauli exclusion principle goes hand in hand. We're going to make sure that each one of these orbitals have one electron in the upspin, and then we're going to double them up using a downspin. So what you need to do is you have to first draw your orbitals, figure out how many electrons there are, fill all the electrons up to the last little bit, and then we're going to be placing electrons in our kind of valence shell, as we will. So let's do an example here. Here we have oxygen, and it's asking us to provide an orbital diagram for oxygen in its ground state. So ground state means that there's no excited electrons. All the electrons are where they logically should be. So the first thing that we need to start off is to figure out how many electrons oxygen has. So if we look at our atomic number, which is right over here, our atomic means that there are going to be 8 electrons here. Now it's not an ion, it's just a regular atom, so 8 electrons. So what we're going to do is we're going to start filling up and kind of going through the rules as we go. So we always start off at the bottom energy level in the orbital, and that's the Aufbau rule. So we're going to put one valence electron in there, and that's shown by the upspin. Now, we don't have any more orbitals here, so Hund's rule doesn't really apply because there are no more orbitals to put electrons in. So what we're going to do is we're going to use Pauli's exclusion principle and double up, giving them different values. So we've used 2 electrons, we have 6 left. So once again, we're going to move up to the next one, and that's the Aufbau principle. We're going to fill up lower ones before we can move to higher ones. So again, we have this. We have no other orbitals that are degenerate, so we put a downspin using Pauli exclusion principle. So again, we use another 2. We have 4 electrons left. So we're going to move up to the next orbital, which is of higher energy. and we're going to put an electron here. Now, what we don't want to do is put an electron over there, because Hund's rule says that we need to populate all the orbitals before we can double up. So let's get rid of that one. So what we're going to have to do is we're going to put 1 in each of these orbitals. So in this case, we've used 3, and we have 1 left. So what we're going to do is now, Pauli exclusion principle and Hund's rule, we're going to put 1 in the first orbital there, and now we are done. So that is the orbital diagram for oxygen. You have 2 electrons in your 1s orbital, 2 electrons in your 2s orbital, and you have 4 electrons in your 2p orbital. Now remember that these are still energy levels, so your 2s are still together. We can treat this as your outer shell, and this is your inner shell. So if you remember back when you started learning about this, the electron arrangement is 2, 8, 8, etc., etc. So here we have 2 electrons in our first energy level, and then in our second energy level, the maximum we could have is 8, but in this case we only have 6. Okay. Now, we can also look at magnetism properties or magnetic properties. Some of these electrons or some of these atoms are slightly magnetic, or actually sometimes slightly repel magnetic fields. So paramagnetism is when atoms are attracted to magnetic fields, and these come about when you have 1 or more unpaired electrons. So as we saw with oxygen, we actually have 2 unpaired electrons. We saw in its outer shell we had this arrangement over here. We had 2 unpaired electrons that didn't have a pair. And so what that means is that oxygen is going to be actually slightly magnetic, and you can actually see this more when you liquefy oxygen. You bring down the temperature of oxygen, make oxygen gas into liquid oxygen, and you can actually start seeing some of these magnetic properties. Diamagnetism is when these atoms are not attracted to magnetic field. In fact, they actually slightly repel magnetic fields, and this comes about when you have atoms with no unpaired electrons. So when you have, for example, noble gases that have full outer shells, these electrons, when you look at the pairs, you can see that one is in an upspin and one is in a downspin. So effectively, they cancel out any magnetic field or any dipole moment that they're going to, or magnetic moment that they're going to have, and therefore they don't have any attraction to magnetic fields. So they're actually going to be repelling against a magnetic force. So just pause the video for a moment and try to create the orbital diagram for this argon atom in its ground state. So once you're done, unpause and you'll have the answer there for you. Okay, so go ahead and pause the video now. Okay, so welcome back. Here's the answer for the orbital diagram of argon. So the first thing that you need to start with is figuring out how many electrons argon has, and that is given to you by its atomic number, which is 18. So once again, we start off with our lowest shell. We put 2 electrons in here. Again, Hund's rule doesn't apply because there's no other orbitals. So we go to the next one, put 2 in our s, so we have 1 s and we have 2 of them there, and we have 2 s and 2. Then we move into our 2p orbitals, and again we put 1 in each orbital first before going back and doubling back, and then we go back, back, back. Now that will fill up that. So actually at this point right here, this is the arrangement for helium. So you have your first energy level, and that looks in the period 1, and you have 2 electrons. That's helium. For here, this arrangement we have is neon. So neon has both its first energy level filled. You have 2 electrons in the first energy level, and then you have 8 electrons in the second energy level. Combined, if we look at this one, you can see that all the orbitals have paired electrons. The entire shell is filled, so you can only imagine this is going to be another noble gas, and that noble gas is in fact argon. Now there's got to be a better way, and some people like using the a filling aid, such as the one over here. So the way that they set this up is just write 1s, 2s, 3s, 4s, 5s, etc. this way, and then move 1 down and start writing 2p, 3p, 4p, 5p, 6p, etc. And then as you can see is n equal to 3, you put 3d, 4d, 5d, 6d, and then n equals to 4, 4f, and 5f. So you can see that that's kind of the pattern here. And what you do there is just kind of go from top to bottom, and you go this way over here. So first thing you go is the 1s, then you go into the 2s. Remember that each orbital can only hold a maximum of 2 electrons. So here you have 1s and you can have 2 in there. You have 2s, you can have 2 in there. Then the next one you fill is going to be 2p and then 3s. After that, you go into 3p and 4s before filling up 3d. And so that accounts for that little overlap that we see. Remember that you got to fill your 4s before you fill your 3d. And then you can start seeing it's a lot more complicated, where you have to fill your 4f before you fill your 5d, before you fill your 6p, and then finally your 7s. So there's a huge overlap over there. But this filling aid helps you with remembering how to do that. Now later on, I'm also going to show you how to use the periodic table to do this, so that will be even a lot easier. But in the meantime, if this helps you, that can be certainly used. So let's look at calcium. Now I'm going to use this filling aid to help me figure that out. First thing I need to know is that there are 20 electrons in calcium. So my first one is I'm going to use my 1s. So I'm going to write my 1s. I'm going to put one up and one down. Now after my 1s, I'm going to do my 2s. So my 2s. And you'll notice how I usually keep the s's in one column here, your p's in another column, and then your d's in another column. So I have my 1s, my 2s. Okay, so next thing I need to go into my 2p's, going over here. So my 2p's will just be offset a little bit. My 2p, and I'm going to put 1 in each. Okay, and that's Hund's rule before I can double back. Okay, so that's right now I'm at 2 electrons over here, 4 here, so that's going to be 10 in total. So I have 10 more electrons to place. So my next step is going to be into my 3s. Okay, and then after that I'm going to go into my 3p and then my 4s. So my 3p is going to be over here, 3p, again 1 in each before I double back. Okay, and right now I have 18 electrons, so I have another 2 to place, and those 2 will be placed into my 4s, so 1 up and 1 down. So now I've used all 20 electrons, and this is my orbital diagram for calcium in the ground state. Now there are going to be some instances where there's going to be something a little bit weird that doesn't kind of follow the same rule. Remember that as we go on, after 3p, we go into 4s first, 3d, and 4p. So when we look at chromium, assuming all other things were filled up, if we look at chromium, if you have a periodic table in front of you, what it should be is we should have 4s, and then we have our 5 orbitals of 3d. Okay, so 4s should be filled based on Aufbau rules, so it should go there. And then you can see that chromium is the 4th element in the transition metals. So you should have 1, 2, 3, 4. So that's logically, based on the rules, how you should see chromium. However, what happens is that one of the electrons in the 4s orbital actually gets promoted into your 3d. And the reason for this is, and the reason for the one at the bottom as well, is that there's a greater stability when the d orbitals are either half filled or fully filled. So that's something beyond the scope of this course right now. But you're going to see some of these anomalies where you're going to have this promotion where you have 4s that's only half filled, and then you're going to have your 3d as a half filled as well, but all the orbitals being occupied. Same thing with copper when we see this, 29 electrons. Now it's the 9th element into the Ds, so if we have our 5 orbitals there, 3D, what we should expect based on the Aufbau is that this one is fully occupied before we move on into the other ones. And so we would have something that looks like this. Oops, not the last one. Okay, what we'd see is based on the Aufbau rule that we would see something that looks like this, with the last one being unpaired. But once again, what's going to be happening is that this electron here is going to be promoted, so you're going to have this completely filled d outer shell with this half-filled 4s. And when it comes to ions, it's not that much difficult. Again, if we look at sodium, remember that ions just have an overall charge. They've either lost or gained an electron. If it's a cation, it means it's lost electrons, become positive. If it's an anion, it's gained electrons. Usually it's a nonmetal, and it's become negative. So sodium is a metal. It's going to try to lose its electron to get that full octet, as we call it, that full outer shell. So you can see that if we look at our 11 electrons, again, we put 1 here. There's 2, 3, 4, 5, 6, 7, 8, 9, 10, and we have 11. So this is, you can see that here we have our third energy level, and it has 1 electron here, and underneath it we have a full 2s and 2p, giving the second energy level a full shell. Now these are your inner electrons. This is going to be your valence electron, and so remember that this electron, this valence electron, is responsible for some of the properties. It's going to be lost, and it's going to form into Na positive. So what does that look like? Well, again, here now, since it's lost 1 electron, it now has 10 electrons. So again, we have this kind of electronic structure, and this one is empty. That electron has been donated to a nonmetal if it's bonding ionic or something like that. Okay, thanks very much for watching, guys. We'll talk to you soon. Bye-bye.